Hi everyone, and welcome to our module on diagnostic tests. In biostatistics, when you talk about diagnostic tests to rule in or rule out disease, the main topics that are usually discussed are sensitivity, specificity, and positive and negative predictive value, which I talk about in other modules. But there are a couple special topics related to diagnostic tests that we're going to cover here, and these are accuracy and precision, ROC curves, and likelihood ratios. All three of these topics are very easy to understand, and if they come up in a board question, they are generally easy points as long as you've heard of the subject and you just know a little bit about it. So let's go over that now. The first two concepts we're going to discuss are called accuracy and precision, and these are both characteristics of a diagnostic test that you can determine by comparing your test to a gold standard. So let's say we knew with 100% certainty through some gold standard test that a person's blood sugar was 120 milligrams per deciliter. And then we had a new test for blood sugar that we were going to evaluate. Well, we would use that test to measure blood sugar and compare it to the gold standard and see how close we got. And from how close or far away we are from the gold standard, we could determine the accuracy and the precision of our test. So accuracy, which is also called validity, is how closely our test matches reality. So if reality was 120 and our new test showed that the blood sugar level was 120, we would say that our new test is accurate or valid. Precision, which is also called reliability, is how closely repeated measurements match each other. So this has nothing to do with the gold standard. But if we do 5 tests of a person's blood sugar and they all come out to be exactly 120, we would say that that test is precise or reliable. It means that we're going to get the same result each time when we use it. And it is possible to have accuracy without precision or vice versa. And the way this is usually explained is by looking at a series of targets. So let's imagine that the yellow in the middle of this target all the way over here on the left side of the screen is the result that we want to get. And let's imagine that this is what we get for our test result when we do it 3 times. Well, we would say that our test result, represented by the X's in the middle of the target, are accurate because they are hitting the center, so they are accurately measuring what we want them to measure. We would also say that they are precise because we've got 3 tests and they're very close together in space. They're not spread out all over the place. So this drawing that I've just made on the left target represents an accurate and precise test. Now let's suppose we get 3 measurements that look something like this. Well, we would say these measurements are relatively accurate because they're hitting very close to the center of the target like we want. So they would be accurate, but they're not very precise because you can see that the 3 tests are far apart from each other. So this test has a problem with precision. Repeated measurements are falling far away from one another. Now let's look at this target on the far right, and let's suppose we get 3 tests that look like this. Well, we would say that these tests are very inaccurate. They're far away from where we want them to be, but they are precise because you can see that the repeated measurements all fall right on top of each other. So what we've got over here is a test that is precise but is inaccurate. And don't forget that the word precision means the same as reliability and the word accuracy means the same as validity. Those terms are sometimes interchanged, and that can be confusing in question stems. So tests that are precise have a smaller standard deviation if you take repeated measurements, and less precise tests have larger standard deviations. So let's look down here at these 2 curves I've drawn. So if this is blood sugar level along the x-axis, and this is the number of times we get each measurement from repeating a test, let's suppose the red curve represents 1 test here. Well, the red curve is getting numbers that are spread out all over the place like this. There's a large distribution of test results. There's going to be a large standard deviation. So the red test is relatively imprecise. The blue test, on the other hand, has a relatively tight distribution of test results around the mean value of 10. So we can tell from looking at this that the blue test results are going to be more precise. And so the better your data measurement is, the more closely you get the same number with repeated measurements, the more precise a test you have. So imagine that you have a machine for measuring glucose and it has random measurement errors. So sometimes the measurements are okay, but then other times it's slightly off. This is called random error. Well, you should know that this is going to reduce the precision of the test because you're going to get some results that are very accurate and dead on, then you're going to get others that are slightly off, but they may be clustered around the result that you want to get. So you may actually maintain your accuracy, but there's going to be lots of scatter of your data, and the thing that's going to be affected the most is the precision. If you have a systemic error, this is going to reduce your accuracy. So for this, imagine that we're measuring people's blood pressure with a cuff, but every time we do it, we're off by 10 millimeters because the cuff size is wrong. This is not a random error like what I described before. This is a systemic error in the data set. Every measurement is off by 10 millimeters. Our precision may be just fine. All those little X's may be very close together, like what I drew on the targets on the last screen, but they're all going to be off from the center of the target because we've got this 10 millimeter systemic error in our measurements. The next concept we're going to discuss are called ROC curves, and ROC stands for Receiver Operating Characteristics. This is actually a concept that comes from World War II, and during World War II, if you were a radar operator, you were a receiver operator, and that's where it got its name. So the point of ROC curves is that different tests have different sensitivity and specificity depending on the cutoff value for the test, and we've discussed this in other modules. If you want to know which cutoff value maximizes sensitivity and specificity, one way to do this is to do an ROC curve analysis. So let's imagine we take some normal subjects and we measure their blood glucose level, and we plot their blood glucose level along the x-axis and the number of subjects who have each measurement on the y-axis. And the normal subjects look something like this blue curve right here. Then let's also imagine that we take some diabetics and we do the same thing, and the diabetics look like this red curve right here. So on average, the diabetics have a higher blood sugar than the normal subjects, but the problem is that the two curves overlap a little bit. So if we want to pick a cutoff value and say that everything above this cutoff value is somebody who has diabetes and everyone below is somebody who's normal, we're going to have a problem, because for any cutoff value we pick, it's not going to be perfect. We're going to get some normal people above that level and some abnormal people below that level. So no matter where we pick this cutoff level, we're going to have a certain sensitivity and specificity of the test. And I talk about this in detail in the module on sensitivity and specificity. But for our purposes here, all you need to know is that we have a series of possible cutoff points from here to here to here to here to here, all the way down here. And for each one of these potential cutoff points, we get a different sensitivity and specificity based on the data from the normal and diabetic subjects. So now let's imagine we take all those different cutoff points and we plot the sensitivity here on the y-axis and 1 minus the specificity here on the x-axis. So why do I choose to plot these two things in an ROC curve? Well, the reason I do is because the sensitivity is proportional to the true positive rates. Remember that the true positive number is in the top of the equation for sensitivity, so the higher the sensitivity, the more true positives we have. And 1 minus specificity, it turns out, is proportional to the false positive rate. The higher this number of 1 minus specificity, the more false positives we are picking up. So by plotting these two things against each other, we are going to get a picture of the trade-off of our test in terms of sensitivity and specificity. And we're going to see if we can determine the best point to use for a cutoff that maximizes both the sensitivity and the specificity. So the worst possible line we could get would be a line that looks like this. And why do I say that? That's because each time we add a little bit of sensitivity to our test, we pay a price of increasing the false negatives. And it's just a straight line like this. There is no value we can pick that lets us get some extra sensitivity without paying a price of an equal amount of false positive test results. So a line that runs straight across the ROC curve like this is the worst possible test result you can get. A better test would look something like this. So what's happening here is that as we move up the sensitivity on the y-axis, we're really not moving very far in terms of false positives. We're adding a lot of sensitivity to our test without paying a big price of increased false positives. Now eventually the curve starts to bend and we do start to get an increase in the rate of false positives, but at least we could operate maybe at a point right here before we've really turned the corner, and we will get a pretty high sensitivity without having a very high false positive rate. An even better test would look something like this. It would allow us to move all the way up to this sensitivity level right here while only paying a price of a very small level of false positives. So the reason I'm showing you these curves is because the thing you need to know about ROC curves is the closer you get to a right angle like this, the better your test. A perfect test that would allow you to achieve 100% sensitivity and 100% specificity would be a perfect right angle that tucked right into this corner of the curve right here. Now no test actually does that, but the more our curves move towards that top left corner like this, the better our test is at distinguishing true positives from false positives. So the key points to remember about ROC curves are that a straight line from the bottom left to the top right is a bad test, And the closer the curve is to a right angle pointing into that top left corner, pointing into this part of the ROC curve, the better the test at discriminating true positives from false positives. And then I mentioned this point before, but let me state it clearly because it's important. The point closest to the top left corner is the best cutoff to maximize sensitivity and specificity. Remember, this curve is generated by plotting different cut points for our test and determining the sensitivity and 1 minus the specificity on the y-axis. The point right here that is closest to this top left corner is the point that gives us the maximum sensitivity while paying the smallest price in terms of false positives. So that point is going to maximize our sensitivity and specificity for our test. One other concept that sometimes comes up is the area under the ROC curve. So the more area under the curve, the better your test is at discriminating true from false positives. So let's look at this straight line here, which remember I said is a bad test. This has half the area of this box under it. So it would have an area under the curve of 0.5, and that's a bad test. This blue curve here has a much higher area under the curve. I don't know what the exact number is, but it's probably something like 0.8 or 0.9, so that would be a better test. If you had that perfect ideal test that could make this right turn and perform a perfect right angle, that would have an area under the curve of 1.0, and that would represent perfect ability to discriminate true positives from false positives and 100% sensitivity and specificity. So just to summarize these points about area under the curve, a useless test has 50% area under the curve, a perfect test has 100% area under the curve, and the more area under the curve, the better the test, the more ability to discriminate individuals with disease from those without. The last thing I'm going to discuss in this module is the concept of likelihood ratios. So let's imagine that we are going to do an EKG on someone to try and decide whether or not they have heart disease. And now I want you to imagine that we could assign a pre-test probability before we've done the test. So imagine we could take this person's age and gender and risk factors and decide how likely it is that they have heart disease even before we've done the EKG. And imagine we could put a hard number on that, like maybe say 30%. Well, after we do the EKG, they are going to have something called a post-test probability. So if the EKG is abnormal, that will increase their likelihood of having disease, and they will have a post-test probability that's higher than 30%. It's probably not 100% because most tests aren't perfect, but it will be something higher than 30. On the other hand, if the EKG is normal or negative, that will reduce their post-test probability. So they'll have a post-test probability that's something lower than 30%. It still won't go all the way down to zero because remember, people with negative EKG still can have coronary disease. It's not a perfect test, but they will have something lower than 30%. So a likelihood ratio tells us how much the probability is going to shift with a positive or negative test for a given patient. So you can define a likelihood ratio if the test is positive, and the equation for that is sensitivity over 1 minus specificity. You can also define a likelihood ratio if the test is negative, and that is 1 minus the sensitivity over the specificity. You probably do not need to know these equations. You should just know that the likelihood ratio comes from the sensitivity and specificity numbers. And some key points I've written down here. These are characteristics of the test itself, like sensitivity and specificity. They do not vary with prevalence of disease the way positive and negative predictive values do. And another thing to know is that you need to know the pre-test probability in order to be able to use these to determine the post-test probability of a patient with either a negative or a positive test result. So this slide gives you a little information on how to interpret likelihood ratios. So a likelihood ratio of 1 means there's no change in probability based on the positive or negative result. Most positive likelihood ratios are very large, so like a number greater than 10 means a positive test carries a large increase in probability. Most negative likelihood ratios are low, so one that was less than 0.1 would mean there's a large decrease in probability based on a negative test. And other results may fall between these extremes, and based on these numbers you can categorize different tests for the same condition in terms of how much they increase or decrease the likelihood of disease. Finally, let me leave you with this one slide and the term likelihood. Don't get confused by this word if you see it in a question stem. If they ask you what is the likelihood of disease in a person with a positive test, they're looking for the positive predictive value. Don't answer the likelihood ratio. The likelihood ratio is a ratio of probabilities and tells you how much the probability moves up or down based on a test result. What they want here is an actual number for the likelihood that that individual patient has disease, and for that you're going to want to answer the positive predictive value. By the same logic, if they ask for the likelihood of disease in a person with a negative test, it's the negative predictive value. If they want the likelihood ratio, they're probably going to ask you directly what is the positive likelihood ratio or the negative likelihood ratio. And for questions like that, remember that these numbers come from the sensitivity and specificity, and remember some of the things I showed you on the last few slides. And that concludes our module on diagnostic testing.